Very nice. So we'll bring that to a larger scale then. This is what we were going to go as if we went to the Mountain Party.
All right. So just let's begin. And so again, here is the schedule for the remainder of the semester. Okay. So there's the current assignment which you're doing a week, and then there's will be one more assignment, which will also be a 2-week assignment. Just because, or is that's one week? Yeah, that's 1 week. Got it. And then the final project. I wanted to talk more about the final project. So it's now, you can download it here at the bottom of the web page. I just wanted to talk a little bit more about it. So again, the assignment is to write a Wikipedia article on some subject of interest to you in quantum optics that includes both theory and experiment. It doesn't have to be one experiment, one topic. It could be a topic with some experiments, one experiment, but should include both theory and experiment, okay? And so it can be, related to an existing page, but your goal is to do something pretty substantial to revise it. If that page is pretty good, then that's probably not the best topic for you. All right? So there's something that doesn't have to be that long, 2 pages to 3 pages, with a figure. Okay, that's the assignment. So what I'm asking you to do is in 2 weeks to send me an abstract, okay? With just a paragraph, that describes what the title of your article will be and at least 3 references that you plan to use, okay? And if there's an existing page to show that, include that, so I can take a look at that as well. And then I'll approve it, or not, in a day, all right? And so you'll have your project, and these are going to be due on Monday, the 8th. That's the Monday of finals. Okay. And I'm leaving on a jet plane on Tuesday, and then we're not allowed to break that while I'm on the plane. I'm allowed to break that when I'm on the airplane. Right. So there's also some links here on how to create this page and the sandbox, and all of the materials that you need are linked here. Okay. And then here's some example topics that I suggest. You can take a look at them, you can think about them, or think about others. But you have a couple of weeks now to get this together. This shouldn't be too onerous, but don't wait till the last minute to get it done. All right, so start thinking about it a little bit. Yeah.
The standard physics and math Wikipedia pages are usually covered in derivations and math. Do you want us to do that type of stuff too, or mostly just the explanation aspect?
I think what I'd like you to do is to have enough of when I say theory, typically the theory involves the appropriate equations that describe what's going on. The details of the derivation aren't important. What's important is the mathematical description of the particular idea phenomenon that you're looking at. So I hope that's enough detail. Yeah.
Are we limited to one figure, or can we?
No.
Awesome.
It just has at least.
Sure.
And it doesn't have to be limited to 2 or 3 pages, but it's not, doesn't have to be a 10-page thing.
Sure. Awesome. Thank you.
Good. All right. Yes.
So how is it being measured in pages if you just scroll?
Yeah. If you were to print it out,
Okay.
yeah, it just gives you a sense of the scale. I'm not going to be word counting. Your margins are not be 11. You know, this is just giving you a scale of what I'm expecting. Very good. Yes, I mean it. Shut it up. All right. Very good. So let's pick up from where we were. So we last time we showed something that's, you know, kind of surprising depending on how you know, were taught and learned about the foundations of early modern physics, modern mechanics, that the photoelectric effect, which was nominally the way in which the idea of a photon was first introduced, can be completely explained without quantizing the field at all. That is, the phenomenology associated with the photoelectric effect, that there is that the kinetic energy of the photo emitted electron is linearly proportional to the frequency of the radiation, and that below a certain threshold of h bar omega, there is no photoelectrons emitted, is completely described by a semi-classical theory, whereby we quantize the matter, but we treat the electric field as a classical field, as we have been discussing for, you know, we discussed for the first half of the semester. And so if we just use Fermi's golden rule, that tells us when we have a continuum of possible states what the rate of absorption is, it has all the properties that I just described. Okay? The h bar comes into Schrodinger's equation, and the omega comes through the time dependence, and there is a resonance associated with absorption near this level, and there's a threshold if I'm above the ionization threshold, which is something called the work function. But there's no hats on my e's here. And what we find is that the rate of absorption is proportional to the intensity. The intensity is the square of the amplitude, with some constant that's sometimes known as the quantum efficiency of the detector. Okay? And moreover, so this is sort of similar to, you know, when Planck introduced his constant, he didn't call it Planck's constant, he wasn't that kind of guy, his idea was that the matter in the walls of the, you know, cavity that made the black body absorbed and emitted chunks of energy. Not that the field itself was quantized, but it's the way, and that's the way in early quantum mechanics people understood, as I have read the history and understood it. And this is what this is going on. The energy is absorbed in these units of h bar omega, but it's not assuming anything about the corpuscular quantum nature of the field itself. And so if we take this as the description, and moreover, we say that this is a kind of quantum jump process that happens randomly, and that different, if we have multiple events, they're completely uncorrelated. These quantum jumps are uncorrelated. That's a postulate of sorts. Then that can fully describe a lot of what one sees in photon counting experiments. So in a photon counting experiment, I might imagine that I have a beam and of light, say, or it could be a collimated source out of a lamp. It doesn't have to be a laser beam, whatever source I have on this. And if I look at, if my photodetector, if this intensity is low enough such that the number of photoelectron events is small within some time window, that's my detection counter, then I'm going to, in each one of those detection windows, I'm never going to see more than one click. I might see 0, I might see 1. And in that kind of Geiger mode, if I looked at the number of counts as a function, or the photocurrent as a function of time, what I'd see is click, 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 random clicks in some sequence. And that random clicks are associated with the random quantum jumps, okay? And we can try to then say, under these assumptions, that I have this rate of absorption, which is proportional to the intensity, and I have these discrete quantum jumps that happen completely uncorrelated. This process of counting occurs, I have random counts in a given time interval. Okay? And the process by which this happens is described what we call a Poisson process. So let me just remind us, or tell you, is we have one S and Poisson or two? Two. Otherwise it's a Poisson process. Yeah. All right. So let's remind ourselves what we mean by a Poisson process. A Poisson process is an example of what we call a stochastic process, which means I have some random variable I'll call n. I'll say it's a function of two numbers, Ta and Tb, which is equal to the number of counts between Ta and Tb that say is greater than or equal to Ta. Okay? And this number of counts is a random variable. That's what we mean by a stochastic process. A stochastic process is a random process as a function of time. Okay? So this is my random variable, and I want to understand the probability distribution associated with under the assumptions that are associated with the Poisson process. And so the assumptions associated with the Poisson process are, one, that this actually only depends on one variable, the time difference between these. It doesn't actually depend on that. It only depends on the difference, the length of the interval, number one. That the counts in disconnected intervals are uncorrelated. So if I ask what's the probability of seeing n counts in this interval and some other number of counts in some other interval, if those two intervals don't overlap, then that joint probability is the product of the probabilities, right? That's what it means to be uncorrelated. The probability, not uncorrected, uncorrelated. So the probability of having some n in delta t1 and n in delta t2 is the product of those probabilities. If these two don't overlap. Okay, is that clear? So that's another property of a, but we're assuming that to be true for our photoelectric effect. Moreover, the average number of counts that I would see in a given time interval is just proportional to the interval, time interval, no matter what interval I'm talking about, okay? So that's another property of the Poisson probability. If I look at the average number of counts in a given time interval, it's just proportional to the time interval, and lambda here is the rate of counts. That's what we would call the rate of counts, is the average number divided by the time interval. And okay, so in our case here, gamma is the rate at which photons are coming onto this. And that gamma in this case would be equal to the power, the rate of energy that's that's the intensity times the area of the beam divided by h bar. So that's the rate at which the photons are coming on average.
You said gamma and real lambda.
I meant lambda.
Okay,
Yeah,
okay.
Yeah. Okay, so these are the assumptions of a Poisson distribution, and I want to then now derive, or just at least show you or remind you how what this gives us is that the probability. So let me define P n comma t as equal to the probability that this random number in that time interval t is equal to n. Okay, so I want to know what's the probability of seeing little n photons in the time t. Yeah.
But can I go to the previous point here? So what do you mean by quantizing the matter? You mean like capacity?
I'm sorry, can you repeat the question?
What do you mean by quantizing the matter? Do you mean like putting hats in like DPG or?
It means that, yes, it means that the motion of the electron is
I
quantized,
see.
right? There are energy levels here. So that means the Hamiltonian that describes the motion of the charges in the material is quantized, but the way that the force it feels is according to a classical parameter with no quantum, okay? So there's a hat here, and there's, these guys. These are my hats.
I see.
Yep, this is a quantum level thing. I'd say there's hats on things that have to do with the degrees of freedom of the matter,
I see.
not the degrees of freedom of the field. We call such a model semi-classical. All right, so with that said, so this is everyone clear what I'm looking at? This is what we mean by the probability distribution. It's the probability that this random variable takes on that value, n, and we want to derive what that is. Well, we can do that by looking at the differential equation. What I'm seeking is a differential equation for this. So I want to know how is P, the probability of finding n photons in a time plus a differential amount related to the probability for that time t. So let's look at the time interval from 0 to t and then t plus dt. These are two different time intervals, okay? So, of course, this is t plus delta t as delta t goes to 0, okay? So the first thing we can see here, of course, what we said before for any interval here, if I have the number of counts in a time delta t, the average of that, by definition, is that, right? Because I said no matter what the interval, this is true. Yeah?
Why'd you say we're looking for the derivative?
I want to find a differential equation so I can solve that differential equation. I want this. But in order to find that, I'm going to derive a differential equation and then solve the differential equation. So that's how we're going to find what this our goal is to find this probability distribution. Okay? The probability system. Okay, so again, this is the case, but if delta t goes to 0, I can only see no more than one photon differentially as delta t goes to 0. That means the probability of seeing one photon in this is lambda delta t, and the probability of seeing 0 in this is 1 minus that. So the total probability. I'm never going to, this goes to 0 as delta t goes to 0. The probability of seeing one photon in this time interval is that. Then, if I add 1 times 0 to that, I get this average. But 2 photons would be something like dt squared. Okay? So this is, so the probability of seeing one photon as delta t goes to 0 shrinks to 0 as delta t. Then it's consistent with my terms. Which means I can say the following. The probability of seeing n photons in this whole interval is the probability of seeing well, by definition, either I saw n photons in the whole interval and nothing in dt, or at most in a time dt, I can see something that has the last photon detected in dt. And because these are uncorrelated, the probability of seeing this and that is just the product of the probabilities. Is that clear? This is the joint probability of seeing n in here and 0 in here, and this is the joint probability of seeing n minus 1 and 1 here. That's all I can get in a time dt. We just said this is equal to 1 minus lambda dt, and this is equal to lambda dt. And so I now have everything I need to derive the differential equation. And I'll just write it down, because I don't want to do the algebra here, because I mess it up and I don't remember it. So this tells me so that's the differential equation associated with this Poisson process. So we have to solve it. How you solve it? You do it iteratively, right? I can first do it for n equals 1, and that'll be related to n equals 0. And then I iterate and iterate and iterate. It's a little bit of a tedious process, but the answer is the following. And you can check afterwards at this. So, what we have shown is that given a Poisson process, the probability of seeing n counts in the time interval from 0 to t is given by a Poisson distribution. So in any given time interval from 0 to t, I don't see the same number of counts. I'm going to see a random number, and they're distributed according to a Poisson process. What is the mean number of photons in this time t? According to this. Close, that's about the fluctuations. Lambda t, right? Because a Poisson process is that, where that's a Poisson process. And this is exactly what we expect, for according to what we just said are the conditions. And the fluctuations, as Kristen reminded us, give us the square root of the mean, okay? So what this tells me is that in any time interval, you name it, here's a time interval, I can say, I can make a histogram, and I can do this photon counting experiment, and I'm going to see a different number each time. If I bin them up, they will be binned up according to a Poisson distribution with a mean number that's just given by the rate at which they're coming in times that time interval, and fluctuations that are given by the square root of this, which depends like the square root of the time over which I'm looking, okay? Now, on this particular thing, I mean, there's a little bit of a subtlety here, and I'll come back to this here. There are two different rates that we're talking about. One is the rate at which I think about photons are coming in, although I'm just calling them photons because I just said there are no photons, or at least this thing doesn't tell me that there are photons. But there's effective rate at which the energy chunks are coming in, and then there's the rate of absorption. So a true detector never has unit quantum efficiency, where every chunk of energy that's there turns into a photoelectron. I can effectively think that there's a kind of beam splitter that is a kind of telling me how to transfer only so many photons that get through. That kind of gives me a kind of transfer function. But if I had that beam splitter, it wouldn't change the Poisson process. It would just say that lambda, the rate at which photons are going, becomes something else that's eta. Eta is some, transmission coefficient times lambda, some fraction. But it wouldn't change the Poisson process, because if I just took randomly photons out of the, if I thought about that, or change the intensity by that, it doesn't change the Poisson process, right? It just means that there's an effective rate that's different. All right, very good. So, but anyway, all right. So, yeah, take his chair. All right. What was I saying? Oh, yeah. So this is when I said that there's this particular lambda, which is the rate at which I assume a particular intensity that is hitting it. But as we know, natural light, or in general, the light that is impinging upon this photodetector, has a random intensity that we don't know. So we really wanted to say something about the probability of seeing n photons, say, in a time interval t. What I would really want to say is, well, there's some probability of seeing n photons given t given a certain intensity, and then I weight that by the probability that there is that intensity averaged over that probability distribution. That gives me the probability of seeing n photons in that distribution, okay? Yeah?
Could you do anything to fix the, how you'd say, the sort of spread of intensities by focusing into the photodetector?
The spatial mode doesn't change the temporal fluctuations. That's just a property of the source.
Mm-hmm.
So you really are not going to affect the fluctuations in the amplitude by its spatial distribution. It is what it is. And you just have to stabilize your laser better. Yeah.
Thank you.
Right, so what this is then is the integral over, the intensities weighted by the probability intensity. And the probability of seeing this then, according to that formula, is, well, now lambda gets replaced by eta times I times t. So this was what I called lambda before, to the power n over n factorial e to the eta I t. Okay. This is called Mandel's formula, after Len Mandel, who is one of the other godfathers of quantum optics. This formula was written down not originally in the context of light, but in the context of cosmic ray type photon kind. It's telling me something about there are Poisson statistics that are associated with the shot noise. Again, I should mention this kind of fluctuation in the number of counts from shot to shot is called shot noise, okay? And it's due to the discrete nature of the absorption. The random discrete events will give me Poisson process and shot noise. So this is what we call shot noise. And this is the fluctuations in the source intensity. Okay? So from this formula, this semi-classical formula, what this would say is that the fluctuations that I would see in the number of counts in a given time interval is at least given by the shot noise. It can never be less than that, because that would require me to have negative fluctuations in the intensity. The least it could be is have no fluctuations, have a perfect intensity, in which case my distribution would be the Poisson distribution, in which case I would see Poisson, this is my shot noise, which is due to the Poisson process. So the fact that the fluctuations are always greater than that is to say that the fluctuations are super Poissonian. Okay, so the semi-classical model here, where we treated the light classically, gives us as a conclusion, and we saw this in other ways earlier when we wrote down a quantum description of the field as a statistical mixture of coherent states, which gave rise to this probability distribution. We came to the same conclusion. So one conclusion is that classical light, which is what is the classical and semi-classical, requires us to see super Poissonian statistics, or at minimum Poisson. But I can never have delta n be smaller than that. If I see delta n smaller than that, Well, that meant that the whole thing broke down and the semi-classical model was shit. I mean, was crap. I mean, was terrible, or wrong. And that's a signature of non-classical light. Seeing sub-Poissonian statistics is a signature that this model is not right. But if it is super Poissonian, we don't need no sticking hats on our electric fields. We can totally treat it as a classical field. Okay. Yes.
So is your effective lambda eta times I in this case?
Lambda in this case is eta times.
I see.
I'm saying that there's some quantum efficiency.
Okay.
But since it's a random process, like there is a chance it will be sub-Poissonian?
Sub-Poissonian is about statistics, not about any one event.
Okay.
So to say that it's to say when we talk about it being Poissonian, it means it satisfies the statistics, which means that all of the moments are consistent with the Poisson process. So any one event, I see a counter, I don't. But that's not saying anything about the process or the statistics. Yes?
So would a coherent state satisfy this condition?
Yeah, that's a good question. What would we say in the case of a coherent state? Would it be consistent with this? Or is that non-classical? Eric is not attending. I agree. Why would you say yes to
Because
this?
the variance is sort of, it's Poissonian.
It is. So, I mean, in a coherent state, then what we have, in that case, we have that the mean n is equal to alpha squared, right? Which is, we could say is the intensity times T divided by h bar omega times the area, right? So that's the number of photons in that thing. So we would have Poisson statistics. We know, we all remember that the coherent state has this distribution. So in that case, it would be equal. The only time it's equal is for a coherent state. If it's not a coherent state, then the state, if it's classical, at least for a single mode, we'll talk about multi-mode, is a statistical mixture of coherent states where P is a probability distribution, like the Gaussian distribution that we talked about for thermal states, okay? That would give us those additional fluctuations are coming from the fact that the intensity is not well defined because the amplitude is not well defined. Is that clear? Good. All right, so the photoelectric effect is out the door as the signature of photons, at least in its usual way. So what would we measure that would give us to say that this thing is really a particle in the end? Yes?
So, you do this, right? And you quantize the matter. But like, let me say historical question. Like back when they were doing this, they were thinking about like more that the matter absorbs energy discretely as opposed to the photon existing. How is it that Einstein figured out it?
Well, I think Einstein said this is consistent. I mean, so let's remind ourselves, we're going to go back and see. I have a longer beard. Okay. Early 20th century, late 19th century, it's called the 1800s and the 1900s. What physicists were really thinking about was statistical physics. The fact that matter itself was corpuscular in nature, that there were molecules, and that there wasn't a continuum of matter. There was no proof of that until later. People, Brownian motion, which is really what Einstein was really, what he really got, cut his teeth on, where he became, science, was thinking about statistical physics, the work of Boltzmann and Maxwell and others. And the fluctuations associated with matter that were associated with the fact that matter itself couldn't be indivisibly divided, but ultimately there were atoms. And so it was in the natural thought, well, maybe the field itself was like that too. What would be the implications of that? So it's worth reading Einstein's paper on the photoelectric effect. I'll send it around. It's you know, the translation of it in not Deutsch, but in you know, English. It's really easy to read, and what Einstein was really trying to do in that paper we worked out on the photoelectric was to rederive the Planck law by thinking about photons in a black body, or think of black body as an ideal gas of particles, and rederiving the Planck law. So this was in the thinking of how, you know, everything was made up of, you know, individual chunks. The idea of an atom goes way back, but the proof of atoms didn't come until much later. Now, from my reading, and everyone should read this, there's a great book written by a guy named Douglas Stone at Yale called Einstein and the Quantum, about the early history of Einstein's contributions. It's really a fascinating book. But, you know, the idea of the photon was sort of out there, but it wasn't really embraced until, from my understanding, until the Compton effect, which really showed it was a billiard ball like. But in quantum optics is another story. So, okay, got the Compton effect. But I want to do something with photons, not X-rays or gamma rays. I want to think about light. And I want to do some experiments that says there are indivisible things we call photons, like atoms. Well, of course, I kind of split an atom as a subatomic thing, but I want to think about it as a unit that I can't divide. It is one particle. It's a particle. What experiment would I try to do to show that this thing is a particle?
Find some minimum amount of energy that you detect.
Well, again, we just sort of did that. That's consistent with this picture. I don't need the particle. It's saying that's really about, you know, the energy has to be above this threshold to ionize the particle. So that doesn't give me this notion of an indivisible quantum.
Can you try to just grab the momentum of one of them?
Well, again, I could think about, it's true that when, say, an atom absorbs light, it also gets a force on it. But again, we can think about that from a classical perspective. Yeah, Omar.
Can we do a polarization experiment and go to single photon level and see that, oh, it goes 50-50 to click or no?
Click or no click? Click or no click? I agree. That's what I want to see, click or no click. So, but I wouldn't think, let's do something, a simpler experiment than polarization.
Is it a double split experiment?
So here's an experiment. I send one photon on a beam splitter. Now, if this is one particle, then if I put two detectors at the two different output ports of this beam splitter, only one of them should go click. If this is one photon under Einstein with Paul Dirac and Liberty quantum mechanics for all, it is never going to go both ways. There's a chance it might go here, there's a chance it might go there, but I'm never going to see that unit of energy absorbed in both of these detectors. Unlike if I had a classical wave here, when I have a classical wave here, some fraction of the amplitude will be transmitted, some fraction of the amplitude will be reflected. I'll always see some intensity here, some intensity here, but if it's a quantum, it can't be divided in that way, which means if I look for a coincidence, so, you know, I put this on a coincidence counter. I should see nothing if it's a single photon. And interestingly, that experiment in this way was not done until 1986. And the experiment was done in the group of the now Nobel laureate Alain Aspect, who did famous experiments on Bell's inequalities. And at the time, one of a very famous guy this was his PhD student, was Philippe Grangier, an amazing guy who might know.
He came, right?
What?
He came to the university.
Aspect did, yeah.
Amazing.
Yeah, he's a friend of mine. It's kind of nice. Anyway, so what does it take to do this experiment? Why wasn't it done until then? The reason is, and it's not that we didn't see other signatures, and I'll come back to that later in this lecture, of non-classicalness. But this particular experiment required me to have a single photon, all right? And that's a hard thing to do. And the source that we now have better sources that can create something that looks like a single photon. But the original source that was used, and the one that was used by Aspect in his Bell's inequalities experiment, was based on an atomic vapor. Okay, yeah.
How is this single photon different from, like, in undergrad I had a single photon experiment and we just attenuated?
Oh, I love that. I'm gonna put a pin in it and we're gonna come back to that. I'm gonna ask you that. It's excellent because we're coming to that. But, okay. So, atomic vapor. So the particular atom they were using was calcium. And it had a particular, the way they did it was the following. So in the atomic level structure of this, there's a ground state. Calcium is in the second column of the periodic table, doesn't really matter, but it's ground state. The two electrons are paired together, as you remember, in the valence shell, so they have a spin 0. And their orbital angular momentum is 0, and so there's no spin, and that has this crazy spectroscopic notation, doesn't really matter, called singlet S0, which just means, that's just a ancient and ridiculous Sanskrit that we still have to use for the spectroscopic notation. That's the ground state. Just means that it's a singlet, the spin of the electron is 0, its total angular momentum is 0, and it's in an S orbital, okay? The ground state principal quantum number is 4. And then they went up to an excited singlet S0. That's not an allowed transition by one photon, but they have 2 photons. Now this state, there's an intermediate state before P1 state, singlet 1 state. And when this thing is in this excited state, it rapidly decays. This has a touch. These states have a lifetime that's very short, and this lifetime of this state is a few nanoseconds. Okay, so these 2 photons come out, so they pump it with light, with 2 photons, and these 2 photons are spontaneously emitted. They're photons their wavelength is around 500 nanometers. They're optical photons, okay? And because the total angular momentum is 0, because of angular momentum conservation and momentum conservation, it turns out that one of these calcium atoms, when it emits these 2 photons, it emits them back to back to conserve momentum and angular momentum with opposite helicities because of the angular momentum. So the details of this don't really matter. We can talk about them more at some other time. The bottom line is this. When you pump this, and you have this 2 photon going, you get photon pairs. In fact, they're entangled, but that's a different story. This was the source he used for Bell's inequalities, okay, because of the polarization, but it's really not so important. What's important is that these 2 photons are born essentially at the same time. They're born within 4 nanoseconds of one another because of this intermediate lifetime, okay? which means if one of these atoms went through this absorption and emission process, this is what's called a cascade, a two-photon cascade. If I detect a photon over here, then I have heralded that within 4 nanoseconds, there's very likely to be another photon. So this is what's called a single photon heralding, and it goes like this. Photon, open the gates, and the gates open, and in 4 nanoseconds, there's going to be another photon. So this is called single photon heralding. Yes, question.
So
Alejandro first.
how do you, for 1 second, anyway, how do you control, I mean, like the photon just exits the atom in any random direction?
That's right. But if I see one here, there's going to be one over here because they're correlated in this way. I don't know where it's going to go, but if I see one here, then there is its fraternal twin that is going to be emitted in the opposite direction with this particular polarization within that time bit. Okay. So I don't know when the birth is going to happen. Their birthday is completely uncertain, but they're born at the same time so they're twins with an unknown birthday. But I wait. So what I do to create this thing is I have a heralding detector. Okay, open the gates. So what it does is I have this counter that opens the gates for some window, say approximately 4 nanoseconds, to now look for these coincidences, okay? And so I have this electronic box that I'm getting photocurrent here and photocurrent here, and it says, look for a click now, when it sees this thing within the speed of light and all of that. It's all timed right. And it looks for coincidences between here. I need to see triple coincidences, because first I have to see this click to know that the photon's going to be here. And then once I see one, I want these two to click. So it's conditioned on this. So there's some rate, I'll call N1, and there's a rate of transmission, and there's a rate of reflection. Yes, sir.
Could I have done this with the SBDC as my source? Because, like,
Yes,
I have
yes.
one path and a
So
single path.
the more modern version of this is three-way mixing through a Kai2 crystal. We'll talk about that next semester. This is a 1, 2, 3, 4-way mixing process that happens in the atomic vapor. And, Aspey was an atomic physicist, so that's why the first experiments were all done with atomic vapors, but later, this is a nonlinear optical process, and we'll talk more about them.
Does the spontaneity of your emission matter here?
The fact that it's spontaneous?
Yeah.
No, it doesn't. It's a bug, not a feature.
Mm-hmm.
It means that I don't know when this photon's going to be, so I have to herald it by knowing that it's there through this. I don't know when I'm going to get this click, but I do know when I get this click,
I should see.
there's going to be that photon. Yeah.
If there wasn't that slight window where it's like, well, okay, we know there's going to be another photon from this window, you wouldn't be able to do that, right? Because you'd be trying to outrun the photon.
That's right. Good. So what they did, there's some probability of being reflected, which is the rate of these counts divided by the rate of heralding. That's the fraction that get reflected. There's a fraction that gets transmitted, and there's a fraction that are coincident. The rate of coincidences. Everything is normalized relative to this rate. And so what they looked at is the ratio of the product of these guys divided by that, or NC, the rate of coincidences times the rate of singles divided by this rate, times that rate. No, the other way around. Okay. And what did they see? They did that as a function of the window that they opened, okay? So if the window was very short, then you're pretty sure that the two photons within 4 nanoseconds were coming from that one process. Of course, there is, 10 to the, 4 atoms or 10 to the 6 atoms in this dilute vapor. I don't remember, it was a hot vapor, maybe it's 10 to the 10th atom. I don't remember how many atoms, but there's millions. And so there could be, they don't necessarily have to be born from the same mother atom, in which case they're not correlated, in which case, one photon could come, there could be 2 different photons that happen in that window, and then I would see one of them might have gotten through and another photon might. So I need to have my window short enough that I'm really only capturing one of these spontaneous events and not multiple of them. So what they measured was a function of that window was this ratio. And what they saw was this. So when the window, there's some data here with error bars on it. When the window is short enough, the rate of coincidences went to 0, which is exactly what you expect. Because if it's one photon, you ain't gonna see no coincidences. It either goes here or it's gonna go here, but you're never gonna see photocurrent in both of them jointly at the same time, okay? Of course, as you increase it, then you have chance of coincidence because they're coming from 2 different photons from 2 different atoms. And so this was an example, all right? The one case is interesting, that's when the probability, it asymptotes to 1, which corresponds to this equaling that, which is to say the probability of coincidence is the product of those. So now I want to come back, take that pin back out, and come back to Tristan's very interesting question, which is suppose instead of doing this complicated mess with, I'm going to go to UNM's undergraduate lab, and what I'm going to do is I'm going to get a Heine laser, and I'm going to put a strong attenuator on this, such that if I were to ask, alpha here is, the intensity of the beam times the area over h bar omega, and I want this to be much, much less than 1. So I'm going to turn down the intensity such that there's almost no photons in this thing. Every once in a while, there might be 1. If there's nothing, I don't care. I won't see any coincidences. If there's 1, I should see no coincidences, okay? And now I'm going to do the same experiment and just looking at the rate of coincidences compared to the rate, I'm looking at that ratio. Now without that normalization, I've done it this way. What do you think you'll see as a function of the time? This is the rate times some w, right? Because this is the rate. This is times that time. This gives me the total number in that interval. So this is the number of photons I would see. This is what I called capital T earlier. This is what I called lambda or eta earlier. Okay. So as I increase this, what do you think you see for the laser? You might think that. It's a reasonable guess. You think same thing. What you see is that the ratio is 1. Now, let me ask you a different question. Let's say I want to look at the semi-classical model. Okay, that tells me that the probability of seeing, I have some intensity coming in. It's a classical wave, okay? Some amount gets transmitted, some amount gets reflected, okay? They're put on 2 detectors, and now I have something that's looking for having both photocurrents together, okay? So according to the semiclassical theory, the rate at which I'll see counts on the transmitted is the eta times the transmitted intensity times that window. That's the rate at which I'll see counts there, right? Which is equal to T times I, right? And the rate at which I'll see reflected photons is the intensity of the reflected one, which is the reflection coefficient times eta IW. Everyone clear on what I'm writing? And what's the probability of coincidences? Well, it's just the product of those 2 intensities. Because that's the rate at which if I see current and current, the rate I'll see both of them is the product of them. And so this ratio, this ratio is 1 at all times. Because there's a fraction that is transmitted, and there's a fraction that's, so from the classical point of view, if these were classical waves, this is what I would expect. But this seems, we just said, with my Heaney laser, this thing mostly had 0 photons. And sometimes it has 1 photon. Yes, someone?
Why is that 1? T and R are both less than 1, right?
But these are both less than 1, but their product is equal to that. So the ratio of this, the ratio of NC dot times these ratios is 1.
Oh.
The ratio of the coincidence count, which is another way of saying the probability of coincidence is just the probability of this and that they're uncorrelated. So why do I see any coincidences at all when I have this highly attenuated light? Yeah.
What is the state of a laser? Like,
It's a coherent state.
So, can we even get a single photon state?
Good question. No, we cannot. It's a coherent state. So why isn't this a single photon state? What we said is that most of the time it's 0. Every once in a while it's 1. But also every once in a while it's 2. And every once in a while it's 3. Now it's true that there's less chance, but the probability of seeing no photons is what? If this given alpha for a coherent state. Probability of seeing no photons. Right? That's a probability of seeing nothing, which is about 1. If alpha is much, much less than 1. So most of the time, it's a little bit less than that. What's the probability of seeing 1 photon? Alpha to the first power over n factor. Remember, p sub n is equal to e to the minus alpha squared, e to the alpha squared to the n over n factorial for a coherent state. Right? You will memorize that.
Okay.
Right. So this is that, which is about alpha. And the probability of seeing 2 is what? So there is always a probability of seeing 2 photons in this thing. And when there are 2 photons, one of them can go this way, and one of them can go that way. And the rate at which that happens is exactly the probability of the rates of this going click and that going click. So Omar's point is the important one. Even though we've highly attenuated this light, it is not a single photon source. And the Poisson fluctuation that are exactly consistent with there being classical waves that are partially reflected and partially transmitted, and then having a Poisson process of counting. I can equivalently, though, so you guys all did your homework. I saw some of them a little late, but fine, they're in the Dropbox eventually. And we know this problem. If I started with a coherent state, let's say this is port A, and this is port B, then if I start with a coherent state in port A and nothing coming in port B, then what's the quantum state on the other side? Right? You start with a coherent state. What you end up with is a product coherent state, and from this point of view, I'll see that. Okay? So, but that's a wave. What we showed is that if I have coherent states that is 100% consistent with the amplitudes of the classical field satisfying the dynamics that we expect classically. But from a corpuscular particle point of view, how do we think about it? What we should think about is the following question. And this goes back to what I was hinting about a Poisson process. If I have a light coming in here with a certain intensity and thus a certain average rate of photons with a Poisson process, and there's a partial transmission such the intensity is reduced by this factor of t, I'm going to see another Poisson process, but just with a reduced rate. Okay? There will also be a Poisson process, but every photon is randomly either transmitted or reflected. I mean, it's kind of both. It's not doesn't happen until we measure it. But I'm never going to see both. So this I can think about from a particle perspective as the following. Lots of photons coming in. Here's the particles, they're random. And every time I do this, I flip a coin. T, I'm heads, I transmit. So this guy gets transmitted, this guy gets reflected, this guy gets transmitted, this guy gets transmitted. So I'm going to see some random, every time I flip, one of these photons will either go this way or that way. Okay? So I want us to think about how this random event of being either transmitted or reflected, how do I think about the joint probability distribution? What's the given this coin flip, which is either transmitted or reflected, what is the joint probability of seeing n photons transmitted sub t and n photons reflected. What's the joint probability distribution of that happening? So I have, let's say the total number is the sum of the two. Okay. So if I have n IID, independent identical runs, I'm going to have n particles, and I flip n coins. Okay. The probability of transmitted is P sub t. The probability of being reflected is P sub r. What is the probability after I flip all those coins? This number will come up heads and that number come up tails. Yes?
Binomial?
The binomial distribution. Excellent, Nate. Thank you. So that's the probability. So that's the probability I have a total number that, say, n sub t of them come up heads times the probability of transmission to the power nt, the probability of reflection to the power n sub r. Okay. Now, I don't know how many photons there are. There is an uncertain number here. So I have to multiply that by the probability of there being n, because that's a Poisson distribution on its own. This, as Nate reminded us, is the binomial distribution. Okay, let's do that out. So the probability of seeing n photons transmitted, or counting n photons transmitted, and n photons reflected is equal to n factorial divided by n minus n sub t factorial, n sub t factorial. The probability of that is the transmission coefficient times I w to the power n sub t. And then I have r I w to the power n sub r, and then I have the probability of getting n photons there is e to the minus I w divided by n factorial I w to the power n.
Do you want to write n sub r as n minus n sub t?
I do, exactly. So we said that the sum, so firstly, this cancels. Okay. This is equal to n sub r. This is n sub r plus n sub t. And so, isn't this pretty? What I see is this is equal to I sub r w to the power n sub r factorial e to the minus let's see. I sub r is r times, this is I sub r, this is I sub t. It's the intensity that's transmitted, that's the intensity that's reflected. No, this was wrong. No, that's.
Is there a coefficient?
Is it because
Oh.
is in both?
No, I see what I'm saying. No, this I can write around as this is equal to 1. R plus T is 1. Okay, now I get it. It's this times that,
Which is just the two.
which is just the probability to Poisson distributions. So I started with a Poisson distribution in all of them in mode A, and through this random flipping, I still have a Poisson distribution, but just with a different rate. So this is, I can think about it, and you should think about it, in these two different ways. In one way, the story of quantum optics is a tale of two cities. It's of the worst of times, it was the best of times. There are waves and there are particles. And we can understand this whole thing in those two different ways. From the wave perspective, some fraction of the amplitude is transmitted, some fraction of the amplitude is reflected. And we'll see these discrete clicks from the semiclassical theory that we just talked about at the beginning of this lecture. Alternatively, I'd say there are indeed photons. They're coming in in a Poisson process randomly. I don't know when they're going to arrive. And then they are divided in a coin flip in a part that doesn't divide the photon in half, but there's some amplitude and thus probability for being reflected, some amplitude being transmitted, and that's exactly like this. It's saying that the original distribution before the transmission becomes a product state of uncorrelated Poisson distributions. And that's why you see this. So they cheated you in your undergraduate lab. It's not really a single photon source. You see something, but you won't get this. Maybe one day we'll have a KTP crystal in optics lab, and we'll be able to do that experiment. Shucks. All right, to be continued. Have a good rest of your afternoon, everybody.